Hello, my dear students, and welcome back to my kitchen and my iPad. I want to finish chapter 3. We had just finished talking about formula mass and formula weights, however you want to term it. And if you know the formula and you know the formula mass, you can also calculate backwards to determine the percent composition, the relative amounts of each element in that given chemical formula. And when we were talking about mass, we briefly discussed the fact that there is a value on every periodic table that corresponds to the average atomic weight or average atomic mass for that element. It's a weighted average based upon the isotopic composition of that element on the Earth's surface or on the Earth. And we used a term called atomic mass unit, which we defined as 1/12 of the mass of a carbon-12 atom. But atomic mass units and weights or masses of atoms are not very useful because, well, for two reasons. One is the numbers. The atomic mass units may be small whole numbers and values that you can work with, but when you convert them to grams, they're fleetingly small. And the other thing is that we just don't work with single atoms or even handfuls of atoms. Atoms are so incredibly small, we work with tremendous numbers of them. So a molecule of water, H2O, here shown space filling with two white hydrogen atoms connected to an oxygen atom. That water molecule, oxygen, has an atomic mass of 16, 15.99994 or something, and hydrogen has an atomic mass of 1.00171 or something like that. I don't have my periodic table in front of me, but for practical purposes, oxygen weighs 16 and hydrogen weighs 1. And so H2O would weigh 2 times 1 plus 16, or 18 atomic mass units. Not very useful. And we don't work with single molecules of water. We work with laboratory volumes, measurable volumes, an 18 mil sample, or a 20 milliliter sample. This is 18 milliliters. And your typical bottle of purified water is 500 milliliters. So, if you consider there's about 25 or 30 sips in that bottle of, on average, 500 milliliters, about 17 fluid ounces, that is a volume we work with all the time. And one swallow, let's say one swallow is approximately 18 milliliters. Well, that volume is one we can work with as well. And water having a density of 1, that also has a mass of 18 grams. But it corresponds to that value that we talked about, that SI unit of the amount of matter present, called the mole. Not named after anything, it's the mole. And 1 mole corresponds to 6.02 times 10 to the 23rd particles. For a pure element, it would be atoms. For a molecular but for a molecular substance like O2, it would be 2 times that in number of atoms. But for oxygen molecules, about 20% of our atmosphere, When you breathe in that air, a mole of oxygen would have 6.02 times 10 to the 23rd, or 1 Avogadro's number of oxygen molecules, which are O2. But it would be 2 times 6.02 times 10 to the 23rd atoms of molecules, because there are 2 oxygen atoms in every molecule of oxygen. So we have this value that is a mole, and it corresponds to an enormous number of representative particles, atoms or molecules, compounds, and it brings it up to lab size in this sense. If you have a mole of water, it has a volume of 18 milliliters and it has a mass of 18 grams. You know, one big swallow of water. Like I said, a water bottle that you would buy of your Ozarka or Dasani or whatever has a volume of about, most of those small bottles have 500 milliliters in them, okay? So 1/20th or so of that bottle, 1/25th of that bottle would be about 20 mils or 18 mils, one big swallow. And that's a usable, measurable amount. We can measure 18 grams, we can measure 18 milliliters. And there's something very unique about those values in both the periodic table for average atomic mass and our formula weights. And that is, instead of using AMUs, we can write them as grams per mole. Grams per mole. So let's move on. The molar mass of 1 mole of any substance we report in grams per mole. For example, 1 mole of oxygen, 1 mole of O2, it'd be about 22.4 liters at room temperature and sea level pressure. It would have a mass of 32 grams, or the molar mass of O2, molecular oxygen, the normal form found in our atmosphere, is 32 grams per mole. Okay, oops, sorry, that's a small L. 32 grams per mole, and that was not a parentheses, that was grams per mole, or over moles. A mole of water, we just said, has a mass of 18 grams, or the molar mass of water is 18 grams, that's a G, per mole. And sodium chloride, made up of 1 atom of sodium and 1 atom of chlorine, a mole of that, or 6.02 times 10 to the 23rd formula units of sodium chloride, would have a molar mass of 58.45 grams. That's calculated like we calculated formula weight. We added the mass of sodium and the mass of chlorine together to get 58.45. And so the molecular weight, molar mass of sodium chloride is 58.45. And what were we adding? Those values from the periodic table. And what are our units when we're done? They are grams per mole. Right there, written much more neatly. So this is very useful. This is what we're going to use for the rest of the chapter. This molar concept and molar mass. And it's important because, like it says here, it provides a bridge from the molecular scale to the real world scale. We have moles, and now we can work in measurable amounts of grams, and we can use Avogadro's number to determine the actual number of formula units for an ionic compound, or molecules for a molecular compound, or atoms for a pure element. And so we use Avogadro's number to find the number of representative particles. I mean, you could technically have a mole of apples if you have 6.02 times 10 to the 23rd. I suspect it would weigh more than the mass of the Earth, perhaps even of the known universe, because Avogadro's number is so incredibly large and atoms are so incredibly small. So let's talk about some mole relationships and just drive this home a little bit. If I have a mole of nitrogen, which if I look on the periodic table has a formula weight or an average atomic mass of 14. And you look on there and you say, what are the units? And most periodic tables won't have any units. They'll have this defined unit, atomic mass unit, which 1 equals 1/12 of a carbon-12 atom, but not very helpful. But when you look up at the periodic table, you see nitrogen has an atomic mass of 14. That means if I had a mole of nitrogen atoms, it would weigh 14 grams, or the molar mass of nitrogen is 14 grams per mole. But you never really have a mole of nitrogen atoms because nitrogen atoms very quickly come together to form a much more stable molecular form, dinitrogen or nitrogen. You know, it's N2. It's a diatomic gas. And so a mole of it would weigh 28 grams. You'd still have 6.02 times 10 to the 23rd molecules. But if you were counting atoms, because there's 2 atoms per molecule, you'd have 2 times that if you were counting actual atoms. When I'm going to go through this table only because I want to make one more point. It's present in the footnote, but if I have silver and I look at the periodic table and the average atomic mass of silver is 107.9 grams per mole, that means if I have a mole of silver, and I would love to have a mole of silver, it would weigh 107.9 grams. It would be 6.02 times 10 to the 23rd silver atoms, but I would have 100 grams or about a quarter pound of silver. Cool. But if I had silver ions, silver dissolved in solution, it would still weigh the same because the mass of those 6.02 times 10 to the 23rd electrons is practically nothing, is insignificant out to 3 or 4 places, okay? So it wouldn't make much of a difference. Here's barium chloride. Barium is a group 2 metal. It forms ions with a +2 charge. Chloride, of course, is a group 7 halogen. It always forms ions with a -1 charge. We'll talk more about that when we talk about periodic trends in the periodic table and chemical reactions. But barium chloride is barium, 2+, and 2 chloride ions, Cl-, coming together to form the electrically neutral barium chloride. And barium's a really heavy metal, and we get a formula mass when we add up the atomic mass of barium and 2 chlorines from our periodic table. We add them up, it adds up to 208.2. 208.2 what? 208.2 grams, that should be a G, per mole, as it says up here in the head of the table. And that would have 6.02 times 10 to the 23rd barium chloride units. And since there's 1 barium atom for every barium chloride, you'd have the same number of barium atoms, but you would have twice that number, see the little number 2 there, of chloride atoms or ions in the compound, barium chloride, in a mole of the barium chloride. But anytime I say I have a mole of something, I know how much it weighs, and I know how many particles I have. And I can work in other directions. If I know how many particles I have, I can tell you how many moles I have. And this can be useful, for example, for determining empirical formulas if you have the percent composition. And there's a way to do this. We'll practice. I'll give you an assignment, a separate assignment with one problem. I'll go over this again. You basically do it this way. If you know your composition and you have your percent composition, you assume you have 100 grams of sample. And then those percentages would be the number of grams of sample for each element. And then we know the atomic mass of each element, so from the periodic table, so we can tell the number of moles of each element we have. Then we look to see what ratios they exist in, and it will at least give us an empirical formula. Okay? I'll run through the quick example, and then we'll do a quick problem on this. I'll show you this again in some detail in a homework video. So, paraminobenzoic acid, also known as PABA, is composed of 61 or a fraction, 0.6131%, 61.31% carbon, or mole fraction, 0.6131 carbon. Hydrogen, 5.14%, nitrogen, 10.21%, and oxygen, 23.33%. And it says, what's the formula for PABA? Boy, that doesn't seem like a lot of information. And it's not, but don't forget, when you're working a problem like this, you also have, or you are armed with, a periodic table. And on that periodic table, you will find your atomic mass, average atomic mass. And you can take that along with the assumed mass, and calculate the number of moles. Okay? I'm also going to show you this later with the little aid called a mole map till you get used to doing this. So, I assume I had 100 grams of it. If 61% of it is carbon, that means 61.31 grams is carbon. Carbon has atomic mass of 12. So if I divide 61.31 grams by 1 mole of carbon, corresponds to 12.01 grams of carbon. In other words, divide it by 12. But what I'm doing here is multiplying it by 1. 1 over 1. 1 mole of carbon is the same, or corresponds to, 12.01 grams of carbon. So in this case, my grams of carbon cancel, and I'm left with moles of carbon. We do it again for hydrogen. 5 grams of hydrogen, if you look in the atomic, not the atomic, but the periodic table, you'll see that 1 mole of hydrogen has an average atomic mass of 1.01 grams. So if I have 5 grams of hydrogen, and it is, 1 mole weighs 1.01 grams, and that means I have 5 moles of hydrogen. Nitrogen has an average atomic mass of approximately 14. And if I have 10 grams, 10.21% nitrogen, but in my sample that I'm assuming weighs 100 grams, if I have 100 grams of sample, and 10%, 10.21% of it is nitrogen, means I would have 10.21 grams. That's going to be less than a mole, because 1 mole weighs 14 grams. So, if you do the math, you end up with 0.7288 moles of nitrogen. And similarly with oxygen, oxygen has an average atomic mass of 16, 15.999 something. But we use 16, and it is 16 out to 2 places beyond the decimal. So, if it's 23% oxygen and you have 100 gram samples, that means 23 grams of that sample is oxygen. Oxygen is 16 grams per mole. 1 mole of oxygen is 16 grams. Means the same thing. If you do the math, where grams cancel and I'm left with moles, then I have in that sample, in that 100-gram sample up here, 1.456 moles of oxygen. And these are my molar ratios. So the carbon and hydrogen are approximately equal, and the nitrogen and oxygen are much smaller, but it means for every 0.728 moles of nitrogen, I have 5.105 moles of carbon. What I need to do is get this in a ratio of 1 to something, into small whole number ratios. And all I do is I divide all of them by the smallest one, okay? When I divide the smallest one by the smallest one, of course I get a mole fraction, or a value of 1. So on our next slide, there's 1 nitrogen, there's 7 hydrogen, because 5 divided by 0.7288 is 7. There's 7 carbon, and there's 2 oxygen. You know, your numbers will not work out perfectly because when we do our elemental analysis, we don't always get perfect results. Oops, sorry, that's an oxygen, not a carbon, O2. So, do you see where our compound would have the formula C7H7O2? And that's our empirical formula. Without knowing the molecular mass, molar mass, atomic weight, many terms, depending on how old you are and what book you're looking at, of the actual compound itself, all we can determine with this method is our empirical composition, the smallest whole number ratios of these substances. These, not substances, these 4 elements: carbon, hydrogen, nitrogen, and oxygen. Okay, that was pretty heavy. We're going to practice one. I'm going to give you 1 problem for your assignment and none on a test. But that was our answer. Now, to do a molecular formula, you need to know the molar mass or molecular weight, as I said. Then you can find the molecular formula. So if someone went ahead and did all that and had an empirical formula, like we just did for that, which, by the way, that also is the molecular formula, but we can determine the actual formula if we're given the molar mass. Let's look at a simple example. We have a compound which is found to be 1 carbon to 1 hydrogen. That's its empirical formula, C1 to H1. Of course, the ones are understood. Well, carbon has a mass of 12.00 something, and hydrogen has an atomic mass of 1 grams per mole. 1 grams per mole. And so it has, we know its overall molar mass is 78. So if we divide 78 by 13, where'd that 13 come? Well, 12 plus 1 equals 13, okay? So we divide it by our mass of our empirical formula, simplest formula, small whole number formula, but not the actual formula, by 13, we get that it's 6, and we end up with C6H6. You know, if it had been CH2 and we got 6, you would say C6H12, for example. And by the way, this is benzene. It's a ring structure of carbon. Each one of these vertices, at each vertex, is a carbon atom, and hanging off of each carbon is a hydrogen. And this is the actual structural formula for a molecule called benzene. There are actually some double bonds in there. But that is a real compound. That's a real example of how, given a lot of information, the empirical formula, the percent composition to determine the empirical formula, and then the molar mass, you can determine the actual molecular formula. In all honesty, these days we are more likely to work backwards. How do you determine those? This was something that was done some time ago when we were determining the molecular formulas of everything. And some elements are easy to determine their composition if there are certain compounds in them. For example, a compound is known to have carbon, oxygen, and hydrogen. And when you burn it, you make water with the hydrogen, when you burn it in the presence of oxygen, and you can absorb that and weigh how much water is produced. And when you burn it, you can measure the carbon because there are lots of ways to easily absorb carbon dioxide and measure its mass. So you take a known mass of a substance, a sample, burn it in the presence of your oxygen, capture the water produced, capture the CO2 produced, and weigh them out. And of course, you had a known amount of samples, so any missing, if there's only carbon, oxygen, hydrogen, would be oxygen, right? So, this is just something that was done a lot. It is relatively straightforward to do these days. I think people would be more likely to use more advanced techniques, spectroscopic techniques, and mass spectrometers for measuring composition. But in a gravimetric analytical chemistry lab, this can still be done, especially useful with organic compounds, of course, that produce CO2 and water. And, that's the way things were done. Let's move on to real stoichiometry and a new concept called mole ratios. Because when we have a reaction, we burn hydrogen in the presence of oxygen to make water explosively, but it reacts very quickly. We say 2H2 plus 1O2, the one that's understood, makes 2H2O. Here it is with pictures of the molecules. But we don't work with molecules. Really, what does this mean? It means 2 moles of hydrogen react with 1 mole of oxygen to produce 2 moles of water. Because we can't really work with molecules, but we can work with moles, because this would just be 4 grams of hydrogen. Hydrogen is 1 gram, average atomic mass. H2 gas would be 2 grams. You need 2 moles of that, so that would weigh 4 grams. Oxygen is 16, but it's a diatomic gas, so molecular oxygen is 32, and you need 1 mole of that, so it would be 32, and the water is 16 for the oxygen, and 2 for the 2 hydrogens, has a molar mass of 18, as we've said several times so far today, and yet, let me go back, and yet this reaction produces 2 moles of it, so we'd make 36 grams of water. And if you notice, the 4 plus 32 on the left for the reactants equals the 36 on the right for the product. So we've followed our law of conservation of mass, and we have a balanced chemical equation. We practiced doing those in the last assignment for the first part of this chapter. And my point is, we have moles, And we can relate that to mass, but what I want to do is talk about mole ratios, because for every 2 of these, I get 2 of these. For every 1 mole of oxygen, I get 2 moles of water produced. So those are the simple, really small whole number ratios we're talking about that are going to be very helpful, because I could ask, for example, if I have 10 moles of water, 10 moles of, say, hydrogen, how many moles of water can I make over here? And I would need my mole ratio. I know for every 2 moles of hydrogen I have, I make 2 moles of water. So if I start out with 10 moles of hydrogen, I'll make 10 moles of water. That's where we're headed. Okay, so we need to convert from grams to moles or moles to grams. We'll practice that. But now, when we're working with this in the context of a balanced equation representing a chemical reaction, we need to consider mole ratios when we're calculating 3 things. And that is, number of moles reacted, number of moles of product produced, the other thing, as you'll see here in a minute, we're going to measure is the limiting reaction. We're just going to do quantities of product and reactant. The limiting reactant, it's often a very important thing to know, and the yield of product produced. So when you are doing chemistry, whether it's in your body, doing reactions in your body, or in a factory where you're carrying out reactions to either break something down to get rid of it or to make something to get more of it, these are the kind of measurements we're interested in knowing, so we can know how much of a nutrient we need and how much we'll be making from that. We want to know what's limiting. Am I getting enough of some nutrient in my diet, and does that yield enough of some product, especially in an industrial setting where I want to make a high-value commodity chemical. So let's go back. How many grams of water can be produced from 1 gram of glucose? Now, your body burns glucose, C6H12O6, in the presence of oxygen through a series of steps, chemical reactions in glycolysis and the citric acid cycle, or the Krebs cycle, or the tricarboxylic acid cycle. Have you learned it? And you produce CO2. You breathe that out with every breath, and water, which you also breathe out a lot in your breath. For example, fogging a mirror. And let's just say we start with 1 gram of glucose. And the question is, how much water will we produce? Well, you always go through the mole. Moles are at the center of our calculations and are the center of our discussions. And if 1 gram of glucose, if you look at this, I have 6 carbons, 12 hydrogens, 6 oxygens. That's 6 times 16, because oxygen has a molar mass of 16 from the from the periodic table. Hydrogen is 12, because the hydrogen atoms from our periodic table have an average atomic mass of 1 for our purposes, and carbon has an average atomic mass of 12, and we would need 6 of those. Well, if you had 6 12s, 12 1s, and 6 16s, you get 180 grams. And that's why I love those values in the periodic table, because I can add up a formula mass, and that's how many grams 1 mole of this, a known quantity, weighs. So valuable. So if I wanted to know how many moles that was, I would just, my grams of glucose cancel, and I'm left with moles of glucose. I divide 1 by 180, and that will give me my value. I'm not sure what it is, because we're just going to keep going and doing more calculations. Because when we look back at our reaction, I don't know where it went. There it is. For every 1 glucose, we made 6 waters. So, for every 1 mole of glucose, I make 6 moles of water. Or to phrase it to match this equation, I make 6 moles of water per mole of glucose broken down. Well, now my moles of glucose cancel, and I'm left with moles of water. And unfortunately, it didn't ask me how many moles of water I produce. I think it asked me how many grams of water I make. So now I need to go back and convert from moles to moles of water to grams of water. But you can see 1 times 6 divided by 180 would end up with the moles of water produced by a single gram of sugar. And that's where this mole ratio is so important for answering questions about these reactions. So, I had 6 moles of water, and I know that 1 mole of water has a mass, or a molar mass, of 18 grams. 16 for the oxygen, 1 each for the hydrogens, or 18 grams of water per mole of water. And again, here and here, I'm multiplying by 1. 18 grams of water and 1 mole of water are the same value. So it's 1 over 1. I'm just, using this method to get to the units I desire. And here, of course, 1 mole of glucose is equal to 280 grams of glucose. Again, it's 1 over 1. So anyway, if you take your original 1 gram of glucose and divide it by your 18 grams of per mole, 180 grams per mole of glucose, and multiply it times your 6 moles of water that are produced per mole of carbohydrate consumed in the reaction. So this is your mole ratio. And you must have what? A balanced equation to get these values from your coefficients. So that's why we started with balancing equations. That's why they're so important. And again, we do another molar conversion. We have 18 grams. We multiply this time by 18 grams per mole of water. The moles of water cancel out, and we're left with grams of water. The moles of water canceled out, and we're left with grams of water. And if you do the math, 1 divided by 180 times 6 times 18, you end up with 0.6 grams of water. So 1 gram of glucose produces 0.06 grams, not 0.06, 0.6 grams of water. Here's a fun fact. What's in a camel's hump? A lot of people think it is water, but it's actually fat stored in there that they burn, and they have a special respiratory system adapted to recovering water because they produce metabolic water as they burn through their calories. They're not burning glucose, they're burning fat, but again, water is produced in that reaction, and you can get significant amounts of water from significant amounts of food. So, when we did this last reaction, and we talked about burning glucose in the presence of oxygen, we made the assumption that there was an excess of oxygen. When we burned our hydrogen and oxygen together, we assumed one of two things, that there was an excess of oxygen or that there were equal molar amounts of it. And if you burn something in our atmosphere, as you use up oxygen, more oxygen floods in, and you have an almost, or practical, in practical terms, endless supply of oxygen. But that's not always the case. What happens when you run out of glucose? You can get more oxygen by taking another breath, but you don't automatically get more glucose. Well, let's look at this reaction where we took 2H2 plus O2 plus 1O2, the one that's understood, and we made 2H2O. So it's only in a test tube or in a reaction flask that you're going to have 2 moles of this and 1 mole of this to produce 2 moles of that. Somebody had to measure these out and provide very precise quantities of these reactants. That's often not the case. So we frequently want to know what the limiting reactant is. Here's an example. I have 10 hydrogen and only 7 oxygen. Maybe I'm in an environment where there's not a lot of oxygen. I'm going to have an excess of hydrogen. And this is going to get used up, actually. I'm going to have, in this case, an excess because I need twice as much hydrogen as I do water. I'm going to have an excess of oxygen. I'm going to have some unreacted oxygen because these 1, 2, 3, 4, 5, 6, 7 oxygens can react with, using my molar ratio, if I have 7O2, here I need 2 hydrogen for every one of those. Here. I'm messing up things so when you come back this won't be visible, but this, I actually, for those 7 oxygens, if I want to use them all up, I need 14 H2s, but I only have 10. So hydrogen was my limiting reactant, and I'm left with excess unreacted oxygen. So in the example, the oxygen would be the excess reagent, and the hydrogen would be limiting. Okay? So what determines how much water I make? The reason we determine the limiting reactant is it determines how much product is made. So I had plenty of oxygen, but only 10 hydrogen. And in our reaction, if I have 10 hydrogen, I'm going to make 10 waters. I might have some excess oxygen, but if I'm interested in how much water I make, I will have unreacted oxygen. But from this reaction flask, reaction vessel, reaction box on a slide, I'm going to make a product, and that product is going to be present in molar ratios determined by the limiting reagent. In this case, it was hydrogen, and the product is produced in equal molar amounts with the hydrogen. So if I start with 10, I'm going to end with 10. So, the theoretical yield is how much product you can make, knowing the limiting reagent. Okay? It's the amount of product possible. When you do an experiment, you know experiments don't always work perfectly. In real life, we have the actual yield, the one actually produced and the amount actually produced and measured. And so that gives us an opportunity to calculate something called percent yield. And percent yield is simply how much we actually got divided by how much we could theoretically get times 100. and we never get the theoretical. So our percent yield is always less than 100. Okay? The higher you get to 100, the closer you get to the theoretically possible amount. And in many cases, that is significant. When I was a Yale Celanese biotechnology fellow working with Celanese Chemical Company, they had a plant in Texas that produced 1 million liters of acetic acid a day. And just an incredible amount. And I don't even know where you would put 1 million liters of acetic acid, especially since tomorrow you need another million. They put it into tank cars and pipelines. But they are working with enormous quantities. And a chemical engineer developing a process that can raise that yield. You know, if they're at a 75% yield and he gets it to 76%, we're talking not millions of dollars, but hundreds of millions of dollars. So these percent yield and theoretical yields and limiting reagent quantities are something that chemists love to work with and love to play with. That's the end of this chapter. I'm going to be giving you 3 quick assignments. One on using and calculating mole ratios and quantities. Given this many grams of this, how many grams of this will you produce? Or if you want to produce this many grams of this, how many grams of this do you need? You'll need to convert back and forth between grams and moles using molar mass, molecular mass, and the mole ratios. And then I'm going to give you 1 or 2 problems in a separate exercise and assignment. And there will be, video homework working through it, video help session working through the homework. I'm going to give you another assignment on limiting reagent. And then another one on yields, percent yields, theoretical yields, actual yields, and put it all together. These are very quantitative, require careful, methodical working of the mathematical operations so that you get the answer we desire. And with a little practice, I think you'll find it's not so bad. So we'll practice together. I will post those assignments at the same time. Hopefully I post this. The last upload I did took over a day from my home, so we'll see what I can get done up at school. And we will start chapter 4 as soon as you finish your assignments for chapter 3. I'll get that posted here presently. Until then, please stay safe and goodbye now.